question about a power bank here, and we are asked to calculate the charge stored when a charge is measured in 1 amp hour, having been told that an amp hour is the charge transferred by a current of 1 amp in a time of 1 hour. So we're using the formula charge is current times time. We can see from our question that our current is 1 amps, but our time is 1 hour. Now the thing to bear in mind here is that we have to convert that 1 hour into seconds. So 1 hour, well, there are 60 seconds in a minute and 60 minutes in an hour. So 1 hour is 60 times 60 seconds, which is equal to 3,600 seconds. When we then plug that into our formula for charge, our current of 1 amp multiplied by our time of 3,600 seconds gives us a charge of 3,600 coulombs. Now a device is connected to the power bank and we're now being asked to calculate the time taken. We are given a current and we are given a charge. So once again, we are using the previous formula, charge is current times time, but this time we're being asked to calculate the time. So we want to rearrange that. So if we rearrange that, time is charge divided by current. So if we take our charge of 3.8 times 10 to the 3, we divide that by our current of 2.4, and we end up with a value of 1600 seconds. However, if you look at the question, it is asking us to give that value in minutes. So we now need to convert that into minutes, and there are 60 seconds in a minute. So our time in hours is 1,600 divided by 60, which actually gives us 27 minutes when you round it up. You can give an answer between 26 and 27. They don't penalise you for your rounding here. Now we're asked to think about the cable that is used in the charging and suggest how this long cable is going to affect the time it takes to recharge the battery when compared with a short cable. Now this is about resistance. So all components will have resistance, but if you have a long cable, that means that a long cable is going to have a greater amount of resistance. Now, what does resistance do in a circuit? Well, resistance obstructs the flow of charge, so it minimizes current. And if you look at how we calculated time earlier, the current that we have affects the time taken. So if you have more resistance in your circuit, you are going to have less current. And if you have less current, then the time taken is going to increase. Okay, so here we're told about the students' 3 devices they want to take on a school trip. And we're told the charge stored in each of these devices and how often they would need recharging. So the student is away for a week and the power bank is storing a maximum of 26.8 amp hours. So determine whether the maximum charge is enough to recharge the batteries of the 3 devices during the trip. So the first thing we need to know here is of that 26.8 amp hours of charge, is that enough charge for the total charge needed during the week? So if we look at this, we work out the total charge. Well, if we say for electronic device A, that is 2.4 amp hours, and that's once a day. So we need 7 lots of 2.4, which is 16.8 amp hours. We've then got once a week for device B. So if we add the 4.2 onto that, and we've also got once a week for device C. So we add 6.8. That gives us 27.8 amp hours of charge needed in total for the week. If we then compare that to the maximum charge that the power bank can store, then we can see that 26.8 amp hours is less than the 27.8 that is required. So now we need a conclusion from that. So actually what we're saying is the power bank can't recharge all 3 if they were flat. However, we have to consider the fact that they may not be flat, so we could get a mark here for identifying that actually the devices won't always be completely flat. And of course, if the child was to use their devices less, that gives us an option for how this would be possible. So you could get a mark for identifying that actually the devices could be used less. And then, of course, there is always the possibility that there are charging facilities available. So the power bank could actually be recharged itself.